So welcome you all back onto this sessions of engineering mathematics actually, and in today's class we'll be progressing to our lecture number 6 of multivariable calculus. Okay, so we basically have a certain multiple, basically we are looking at the concept of multiple integrals, and we have also seen the concept of change of order of integration, right? So in today's class we'll extend this discussion to of course two-dimensional integrals and also 3D, basically the volume calculations, and also we'll talk at some applications of multiple integrals actually here. Okay, so let's see and before I start away the session, I would like to give you a quick update on the Telegram channels where the content on this channel is being posted. So do follow this Telegram channel so that you won't miss any content that's coming out on this channel. Okay, so you'll be in sync with all the lectures. And also this is our Telegram group, basically the personal Telegram group of mine, managed by me and my students as well. So this any update by me will be posted here, and if you want to get in touch with us, the student community, then you can definitely scan this and get in touch with us. Okay, and I also advise you to install this PW Unity so that you have a single stop place for all your important points, notes, doubts, and all the things. Okay, and of course once you start typing that out, if you type exclamation doubt, and as well as if you want to write a note point to save in Unity, you can type exclamation notes actually. So this will actually save in a particular place of the PW Unity actually. Okay, so let's see, in the last lecture we were talking about multiple integrals. We were talking about the multiple integrals, and the integrals are of the form I is equal to integral, like say for example x is equal to some function of y, to x is equal to say some other function of y maybe here, then y equal to alpha to y equal to beta, then you have the function say h of x comma y dx dy. So we have seen you can convert this integral into another 2D integral, of course, by changing the limits. Okay, so the main focus in today's class was on calculation of multiple integrals and exclusively writing the limits of the integral. Okay, so writing the limits of the integral actually, writing the limits of the integral. Okay, so let's see, in today's class we'll be looking at the concepts of application of this multiple integrals and coordinate transformations. Of course we'll also involve some 3D integrals, basically integrals in 3 dimensions, so that we can do some calculations like volume, centroids of volume, this kind of stuff. So we will see, and also we'll see the coordinate transformations, like let's say if you have an integral in Cartesian, then how to convert this to, how to convert this, just a second guys, I think there is slight issue here, video. Any issue that's coming up? Okay, fine, everything is fine, right? There's no issue, audio or something. Yeah, so let's continue. I hope everything is fine. So let's see, so we also do the coordinate transformations. So if you have an integral in Cartesian system, we'll also convert that to cylindrical coordinates, or if you want to convert that to spherical, we can convert actually. Also, if time permits, I'll also give a certain introduction to differential equations in today's class. Okay, so before I give this, in the last lecture I have given you some homework, so let us have a look at that particular homework. Okay, and I'll run the poll so that you can just solve that. Okay, so this is the question which I have given you as homework in the last lecture. So if some of you have solved it, enter the answer. So you can enter the answer. So actually I know we shouldn't ask this doubt as this math class, but I have doubt in applied thermodynamics. There we have intercooling or gate, sorry, whether we have intercooling, regeneration. No, regeneration we don't have. Okay, reheating we have, but regeneration is not. Okay, good evening all of you. Just enter the answer if you have solved this question. Okay, regeneration you don't have for XC. So let's solve this question now. So directly if you make an attempt to solve this question, it would be slightly difficult in order to integrate this. Okay, so let's say let I is equal to integral 0 to pi integral y to pi, of course y to pi, integral y to pi sin x by x dx dy. Okay, and clearly you can see there is a function of y here, so which means these are x limits clearly, and the limits on the outer integral are y limits, and this integral is given as per this syntax. Like you can see this inner integral has x limits, so the first variable of integration is also x, but integrating the function sin x by x is not very easy thing. Okay, so you have to go for, again, basically sin x by x integration is not something which you can write directly. So what we can do, we can actually do the concept of change of order of integration. Okay, so by change of order of integration, so if you change the order of integration, so let's see how do we get this. So change of order of integration, first of all, what are the curves involved? Curves involved are, so what are the curves involved? X is equal to y or y equal to x, whatever. X is equal to pi, y is equal to 0, and y is equal to pi. So let us focus on the region which is bounded by these curves actually. Okay, so if you plot that, we have x-axis, then y-axis, of course. Then let's see, first y equal to x. Okay, so let's say y is equal to x, line is something like this. So this is y is equal to x actually here. Then x is equal to pi, so x is equal to pi is something like this maybe. So x is equal to pi is something like this, x is equal to pi. Then y equal to 0, which is nothing but this x-axis is actually y is equal to 0, and y is equal to pi. So if you take y is equal to pi, then you have the line something like this. This is y is equal to pi. This line will definitely pass through this point of intersection. Okay, this will definitely pass through this point of intersection. The reason being, if this is x is equal to pi, and if this is the line y equal to x, then this is the point of intersection, pi comma pi. So y is equal to pi is like this. Now try to tell one thing. You have two regions, first region and also second region. Now out of these two regions, which region should I consider? Please tell me. So please type in the chat box, out of these two regions, 1 and 2, which region should I consider and why? Or basically, first of all, tell me which region you should consider out of region 1 and region 2. Piyush, Mallikarjun, Ajit, Pavan, every one of you in fact. So please tell me why, or basically which out of these two regions, 1 and 2, which region I should consider. For my domain. So quick, a bit faster. Region 1, is it? Yeah, of course, you should consider region 1. The reason is, this region 2 is actually bounded by this y-axis, but the equation of y-axis is x is equal to 0, but you cannot find x equal to 0 in these curves. Okay, so the region which is bounded by these curves, and x is equal to 0, which is y-axis, is not present in any one of this equation. Okay, so in fact this region, so the y-axis what you have done is just for your reference, but in fact this is not bounding any region. Okay, so this region is not bounded. So this is the only region which is bounded then. So let's see, if you want to change order of integration, then the first variable of integration in the actual integral is x. So upon changing, the first integral becomes y. Now tell me one thing, if I decide to make y as my first variable of integration, should I consider horizontal step or vertical step? Come on, tell me this. So I is equal to, meanwhile alert, if I consider y as the first variable of integration, in this region, should I consider horizontal step or vertical step? Come on, tell me. I equal to integral f of x comma y, which is sin x by x. I am interested to write dy dx. Then in such case, which step should I consider? Y is my first variable of integration, so ultimately I should write y limits. Now if I want to write y limits, then I should consider horizontal step or vertical step. Y is my first variable of integration. If y is my first variable of integration, then I should consider my vertical step, right? So if you consider this vertical step actually in this region, okay, so this is the vertical step you have, then you move this anywhere in this region, the lower bound is always given by y equal to 0, and the upper boundary is always given by y equal to x. Okay, so this is what you get, y is equal to x actually. Now what about the lower, least and maximum values of x in this region? The least value of x is here 0, and the maximum value of x is here at this point, which is pi. So x is equal to 0 to x is equal to pi actually here. That's it. Okay, so in the last class we were repeating, so we should consider the vertical step, right? Yes or no? In the last class I was telling, if you take y as the first variable of integration, you consider a vertical step, and if you consider x as the first variable of integration, you should consider the horizontal step. We were talking in yesterday's class, you remember? Basically I'll open the notes, maybe you might have forgotten something. Let's look at it. So downloads, and in the last lecture we were talking about this. Okay, so yes, when I'm talking about the multiple integrals, which you can see, of course, now you see, whenever we have taken the first variable of integration as y, we have considered vertical step. Okay, so similarly, when we have changed the order of integration later, this concept of change of order of integration was discussed, and when I have taken the first variable of integration as x, which you can see here, I have taken the horizontal step actually. Okay, so that's what we mean. Fine, Ajit, Sujay, Shravan, Piyush, everyone. Okay, right. Okay, fine. So if y is first variable of integration, we consider a vertical step in general. Okay, so we consider a vertical step. We consider a vertical step actually here. Okay, so that's fine. Yes or no? Please type it in the chat box. Now let's see if I consider a vertical step. So this is the integral. So let's first evaluate this integral by treating x as constant. So if x is treated as constant, the integral value is x is equal to 0 to x is equal to pi. Then when you are integrating with respect to y, this complete function is a constant, sin x by x into, so integration of you can write 1 here maybe, so 1 into y is y, and this y has the limits 0 to x actually here. Okay, so dx. So ultimately when you substitute limits, this value becomes x minus 0. Okay, so when you write upper limit x, when you write lower limit 0, so x minus 0 is 0. So this x and this gets cancelled. Okay, because this is also x actually when you substitute the limits. Got it? Yes or no? Is this step clear to all of you? Normally this sin x by x is a constant when you are integrating with respect to y. So treating the sin x by x as constant, integration of 1 is y, but the limits of integration are 0 to x actually. So 0 to x, if you substitute, this value would be x minus 0, which is x. So this value and this x gets cancelled. Okay, so is this clear to each and everyone? So ultimately then this integral gets converted to integral 0 to pi sin x dx, so which is minus cos x within the limits 0 to pi. So this value being something like, if you take the minus sign out, cos pi is minus 1 minus cos 0 is 1. So this answer is 2 actually here. Okay, so this answer is 2. 2 is the actual answer of this integration. So this is equal to 2. Fine, got it? This x gets cancelled up because of doing the integration. Okay, then it's easy to integrate. But if you choose this value of x as the first variable of integration, it's not very comfortable. It takes so much time to evaluate the integral. Okay, fine. So the answer is 2 actually here. So let's see if some of you have entered 2. Oh, some of you have entered. Ashwini, good. Okay, let's see. Let's solve one more question. I'll give you one more question now based on the concept of change of order of integration. You know how to solve this. Come on, solve this. If I is equal to integral x equal to 0 to 1, y equal to 0 to x square, xy square dy dx, then I may also be expressed as one of these following forms. Okay, so I will give you some time. Single choice question, maybe 150 seconds I'll give. Start. Do this question. The poll is active. So this is the actual integral I. So you have changed the order of integration. Okay, do this. For any integral, as long as the function is continuous, you can for any question, for any question you can apply change of order of integration, but in general few questions can be directly calculated easily. Okay, please, sorry to ask this again, sir, do we have intercooling in Berton cycle? Intercooling is very small concept. If you want, you can study now better. Okay, let's take safe side and let's say it is there in the syllabus, because intercooling is like very easy topic. Okay, just you cool the air in between the compressors, in between the stages, to reduce the work input. Okay. Anyhow, if you write for mechanical, intercooling, regeneration, all these things are there, so just study for that. Because sometimes they can ask you questions based on the optimal intermediate pressure for recooling. 1 mark questions too. Better not to skip. Okay. Come on, quick. All this. Yeah, just study intercooling. Okay. better. Okay, so doing this last 1 minute roughly. Done? Yay, maybe. Okay, so let's see. First of all, by looking at these options, two options can be eliminated always. Can someone tell me what are the two options you can eliminate? By looking at these options, you can tell the two options are definitely not the answers. What are they? Can someone tell me? Two options are not definitely answers. You can eliminate two options. What are the two options you can eliminate? A you want to eliminate, or A is the answer? So let's see. When you do the transformation in general, if you have y is equal to some phi of x to psi of x, whatever, and x is equal to a to b, let's say you have the function f of x comma y dy dx is equal to integral y is equal to c to d integral x is equal to say some alpha of x to alpha of y, actually we write it in terms of y, so alpha of y and beta of y f of x comma y dx dy. This is what you write. Okay, by changing the order of integration, okay, so by changing the order of integration, all the four limits gets changed, but will the function change? Will this function, whatever you have to integrate, will this function change? I'm not applying transformation, I'm just changing the order of integration, okay, in the same coordinate system. Then will this function change? Please type it in the chat box. Can anyone tell me, will this function change actually? Shravan, Santosh, Ajit, Piyush, any one of you. Will this function change because of change of order of integration? Only the limits change, correct? Limits on the integrals change and the first integrating variable changes, but the function do not change. So, but here in this question, the function given is xy square, but here it is x square y. Okay, so this function cannot change, obviously. So these two are definitely wrong options. Okay, then let's see. So B and D you can eliminate. Good. So let's see. Out of these things, how we can write. I is equal to, given integral is I is equal to integral x is equal to 0 to 1 and y is equal to, so y is changing from 0 to x square, so y equal to 0 to y equal to x square. So some function you have which is like xy square dy dx. So now let us plot the curves. So what are the curves you have? So curves are y equal to 0, y equal to x square, x is equal to 0 and x is equal to 1 actually here. Okay, so x is equal to 0 and x is equal to 1. So let's plot the curves and identify what do we have. Origin x y. So first curve y equal to 0, which is x axis, we have already plotted. Then y equal to x square, so y is equal to x square, so y equal to x square is something like this. Okay, general you have the parabola of course. So yeah, okay, fine, let's draw a freehand sketch. So something like this. Okay, so I take, of course, I'm a very bad artist, but bear with me. Fine. Okay, so this is y is equal to x square. Let's say this is y is equal to x square curve. Then x is equal to 0, which is y-axis. X is equal to 0 is y-axis. X is equal to 1. X is equal to 1 is somewhere here. So let's say this is somewhere here. X is equal to 1 is something like that. So if this is the curve, x is equal to 1 actually here, then if you try to identify the region which is bounded, only this part is bounded, which is in between this y equal to x square, x equal to 1 and y equal to 0. Only this region is bounded actually, correct? So let's see. In this region, because the region is bounded is towards the positive quadrant, positive value of x. So if y is equal to x square, this implies this equation is actually x is equal to root y, correct? So y is equal to x square, which implies x is equal to root y. And this is x is equal to 1, of course. Okay. Now if you want to change the order of integration, changing order of integration, what do you have? See, I is equal to integral x is equal to something to something, y is equal to something to something, the function as usual xy square dx dy. Now tell me, if you want to have x as your first integrating variable, the step that I should consider in this region is horizontal or vertical? So please tell me, if I want to consider a step in order to have x as my first variable of integration, then should I have my step to be horizontal or vertical, this region? Come on, quick, a bit faster. A bit faster, please. I've just told you something. If variable of integration is y, first variable of integration is y, I have written something here when I'm solving this question. If y is the first variable of integration, we consider vertical step. Okay. So if you consider x as the first variable of integration, within this region, the step you have to consider is vertical or horizontal. Please tell me. Be horizontal step, right? So we take a horizontal step actually. We take a horizontal step in this region. So this is the region which you have. Now, and ultimately the domain which is bounded is of course this domain. Along this y is equal to x square, this point along this line, and you have closed loop. Okay, so that's the loop. Now, whenever you move this step anywhere in this region, the least value of x is always bounded by this equation, x is equal to root y, and the upper bound of x for this step is always given by 1. So the least value is given by x is equal to root y, and upper value is given by x is equal to 1. Okay, and now what are the minimum values of y? Y is minimum at any point on this line, of course. So 0, and this value is when x equal to 1, y is also 1. This point is 1 comma 1. So in this region, y is going from a minimum of 0 to a maximum of 1 actually here. So y equal to 0 to y equal to 1. That's it. Okay. So without actually calculating the value of the integral, just by applying the concept of change of order of integration, we figured out that this integral is equal to 1 of this, and ultimately if you check here, x is equal to root y to x is equal to 1. So this option is wrong. It's not 0 to root y, it's root y to 1, and y is also going from 0 to 1 actually here. Okay. So option C is the correct answer. Got it? Yes. Is this clear to each and every one of you? The correct answer is actually C in this case. Yes or no? See, writing limits is the main important part, which I have already told yesterday. When you are writing this integration with respect to x as the first variable of integration, in this horizontal step, you'll see when you are moving this step in this complete region where you have the least value of x. Least value of x is always given by this value of curve, which is x is equal to root y, and the maximum value is always given by this limit, which is x is equal to 1 actually. Okay, so x equal to root y to x equal to 1, and of course the least value of y in this complete domain is 0, which is at any point on this line, and the maximum value is 1 actually. So y changes from 0 to 1, and that's how this integral can be converted to this integral. Okay. Yes, is this clear to all of you or not? So let's solve this. C is the correct answer. Okay, so many of you, some of you have written A, some of you have written B. Okay, B is also taken, good, but actually C is the correct answer. Okay, because of understanding. Fine. Sujay, Ajit, Santosh, Shravan, Shrikant, Piyush, every one of you. Okay, so let's see. So this is the case. Then first let us look at some application of multiple integrals. So applications of multiple integrals is first, or basically if f of x comma y is a function, is a continuous and differentiable function, is a continuous and differentiable function, is a continuous and differentiable function in a domain D, in a domain or a region R, let's say a region A, whatever you want. Okay, so in a region A, then first one, integral over a f of x comma y dx dy or dy dx, depending upon whatever the limits you write, gives, so this gives area of domain D, area of domain region A, let's say area of region A if f of x comma y is equal to 1 actually. Okay, so if f of x comma y is equal to 1, so which means if this is actually 1, then this becomes double integral a dA. I have told you, when you take a small elemental rectangle of length dx and height dy, the area of the small rectangle is dx dy, and if you integrate it over the complete area, you get the total area of the region. Okay, so which we have seen. Second, point number 2, integral over a f of x comma y dy dx is equal to area into x bar if f of x comma y is equal to x actually here. Okay, where x bar is x coordinate of centroid of region A actually. Region A. In fact, in last class I have shown you one of the example by taking some triangle which we have solved, like since I have the notes here. So yeah, for this case we have calculated integral x dA. Okay, in the case of y I have shown you the simple calculation. Yeah, based on this logic is what I have told you. So once we have calculated this integral using this integration technique and we got the answer to be 729, but by multiplying area with x coordinate of the centroid within a single line, we also got the same answer, 729. Okay, so this is what you get. And third, integral over a f of x comma y dx or dy dx whatever is equal to area into y bar if f of x comma y is equal to y actually. Okay, and where y bar is centroid is y coordinate, y bar is y coordinate of centroid of region A actually here. Okay, so this is of region A. Fine. So let's see both. This time I'll ask you something different. Integral x square dA or x square dy dx whatever. So this function f of x comma y is x square. So can someone tell me what is this? What does this gives you actually? If you have an area A like this, so x y, and let's say you have the domain omega. Okay, area A. So let's say this is area A, of course. Then in such case, if you calculate a small elemental strip dA, and let's say from this y-axis the distance of this is x. So if you calculate integral x square dy dx, then do someone know what does this gives you? With respect to y-axis, the distance of this small elemental area dA is, this is dA for example. So dA is x actually. So this distance is x. So if that distance is x, then integral x square dA, what does it gives you? Come on, type it in the chat box. Integral x square dA, what does it give you? Any idea? No idea? So this actually gives you moment of inertia. Of course, area moment of inertia, let's be specific. Again, some of you may feel mass moment of inertia. So area moment of inertia, area moment of inertia of region A about y axis, and normally this is written as I y is equal to integral over a x square dy. Okay, so that's what you have. Then fourth, similarly, if you have, this time you may say, I think, integral over a y square dy dx. This gives you area moment of inertia of region A about x axis. So this gives you about x axis. Okay, so clear, this is about x axis. So let's see, still you have many of the things. Integral over a xy, if the function is xy, then this gives you product of inertia of region A about origin actually. Okay, so in fact you can keep generating lot many complicated applications as well, but normally the day-to-day examples which we encounter in all the technical subjects is using one of these things. Okay, using double integrations, then this function is either x square y square, calculating moment of inertia, all these things. Okay, so let's try to solve one example actually. Example, let's say example, the value of integral over a x square or y square dA, anyway it's symmetric, no issue. So y square dy dx, let's say, or dx dy, whatever, depending on the limits you write. So the value of this integral, where a is the region of first quadrant of the circle, first quadrant of the circle, first quadrant of the circle, say x square plus y square is equal to a square. Okay, so let's say the radius is a, of course. So the radius is a, so let's say, so x square plus y square equal to a square. So let's say I have to calculate this integral over a, y square dy dx is basically dA, of course. So x square plus y square is equal to a square. Okay, so we'll solve this question using classical technique of evaluation of multiple integrals. Then once I show you the coordinate transformations, we will see how coordinates get transformed. Okay, means solving this question actually, of course everything is in Cartesian, but solving this question in polar is very easy. Okay, which I'll show you after transforming this Cartesian integral to polar integral. Okay, by transformation actually. So let's see, initially if you want to solve this question at this stage, the classical way that you do this question is take x-axis and take y-axis as well. So take y-axis, so origin x y, so you have this curve. So let's say x square plus y square is equal to a square. Fine, so let's say this is the curve x square plus y square is equal to a square actually. So the region which is bounded is undoubtedly this x-axis, this y-axis, and everything which is inside this blue colored curve. So everything inside this blue colored curve is the region which is bounded, right? Now if you want to evaluate this integration, let's see how do I do this. Solution, I is equal to integral y square dy dx. So what shall we consider the first variable of integration? Should we go as this? Okay, if you want, you can change, you can change the order of integration, doesn't matter, in both the cases you will get the same answer. So let's say if I maintain y to be my first variable of integration, then you should tell correctly now, otherwise I'll kill you. So if y is the first variable of integration, which step should I consider here, horizontal or vertical in this region? If y is the first variable of integration, then the step I should consider in this domain D, or basically in this region A, is vertical or horizontal. First variable of integration is y. Okay, then it should be horizontal step or vertical step? Vertical. Okay, good. So it should be vertical step. So let's consider a vertical step to understand the story. So if you consider this vertical step, now you move this step anywhere in this region, the lower bound is always given by y is equal to 0, and the upper bound at any point is given by y is equal to root of a square minus x. You may ask me, why are you not considering the minus sign? Because I know I'm situated in the first quadrant. So if I am sitting in the first quadrant, y is always positive, so I'm not taking the negative sign here. Okay, I'm taking y to be positive. So whenever you move this strip at any location, the lower bound is given by y is equal to 0, and the upper bound is given by y is equal to root of a square minus x square. Okay, then in this complete domain D, the least value of x, so least value of x is at any point on this line. So basically x is equal to 0, and the largest value of x in this domain is x is equal to a, of course, because when you put y equal to 0, x is equal to a. So x is going from 0 to x is equal to a, and we shall integrate now. Is this writing limits clear to all of you? Please confirm. Shrikant, Sujesh, Shravan, Ajit, Santosh. I could read only these names. All went. So please type it in the chat box. Is this writing of limits clear to each and everyone? Did you understand why x limits are from 0 to a? Because in this complete domain, the least value of x is 0 at this end, and the highest value of x is at this point. Okay, so x equal to a actually. So let's see, if you calculate this integration, it gives you I is equal to integral x is equal to 0 to x is equal to a, of course. Then if you integrate this with respect to y, it's like y cube by 3, correct? So it's y cube by 3, obviously. Integral 0 to root of a square minus x square dx actually here. Okay, so this is what you get, dx. Then let's try to simplify this. Integral x is equal to 0, 1 by 3 times of x is equal to 0 to x is equal to a. So if you substitute this, root of a square minus x square whole cube, so this is a square minus x square whole power 3 by 2 dx. Okay, because when you put 0, it is 0 cube is 0. So this is the integral what you have. Yeah, I'm repeating once. Normally, once you have these limits, if you integrate this, okay, your doubt is writing x is equal to 0 to x equal to a. Okay, so in this complete domain, like I have always told you, if this is x and if this is y, and let's say your geometry is something like this, then out of all these points, the least value of x is at this point, and the greatest value of x is somewhere here. So this is the point, x is equal to b. So we write x is changing from a to x is changing to b. So likewise, in this complete domain, the least value of x is basically at any point on this line. So x equal to 0 is the least value, and at the highest point, this region has the complete highest point at this spot. So x is equal to a is the value. So the lower value is x equal to 0 to x is equal to a is the upper value. Okay, upper limit, of course. Correct. So wherever you take a point in this region, ultimately the least value of x is obtained here, and the highest value of x is obtained here. That's it. Fine. Yes or no? Is this clear to all of you? Please type it in the chat box. Okay. Then if you integrate this, so let's say if you want to integrate this guy, how to integrate? So let's use a trigonometric substitution. Let x is equal to a sine theta, maybe a sine theta. This implies, okay, so let x is equal to a sine theta. So this implies x square minus a square is equal to a square cos square theta, of course. Okay, so that's what you have, right? Obviously, because, oh, just a minute, I think a square minus x square. This is not x square minus a square, this is a square minus x square. The reason is a square minus a square sine square theta. So if you take a square common, 1 minus sine square theta gives you cos square theta. What about dx? So dx gives you a into derivative of sine theta is cos theta d theta. So you have a d theta, of course. And what about the lower limit? So lower limit value is x is equal to a sine theta, and the lower value of x is 0, of course. So the lower value of x is 0. So 0 is equal to, so 0 is equal to a times sine theta, and a is non-zero, obviously. So theta is 0 within this domain. Okay. And what about upper limit? A is equal to a sine theta, because x is equal to a sine theta. So we have done these substitutions and all in single variable calculus. So this tells you theta is equal to pi by 2, of course. Okay, so theta is equal to pi by 2. So if you convert this substitution, we end up with something like I is equal to so integral, okay, 1/3 times integral. So this in the new system, or basically in the new substitution, the lower value got converted to 0 actually. Okay, theta equal to 0, and upper limit got converted to pi by 2. So theta equal to pi by 2. So theta is equal to 0 to theta is equal to pi by 2. Then after a square minus x square whole power 3 by 2. So what is the value of a square minus x square? A square cos square theta whole power 3 by 2. Cos square theta whole power 3 by 2 actually here. Then dx. What is dx? A cos theta d theta. Okay, so we have a cos theta d theta of course. So if you simplify this result, I is equal to 1/3 times, look, this squares can actually be cancelled with this half here. Okay, so we have a cube and a, so total a power 4 into integral theta equal to 0 to theta equal to pi by 2. This is cos cube theta and this is cos theta, so cos power 4 theta d theta. Okay, so cos power 4 theta d theta, and clearly you have reduction formula to write this answer, right? A square minus x square is equal to a square cos square theta. How? Substitute, no? Okay, fine, like this. Just substitute, you will get the answer. Okay, Shravan? Yeah, is this clear to all of you? Because if you just substitute x is equal to a sin theta here, then it becomes a square cos square theta. Like basically this term is something like, okay, it's just a bit of funda, so I have just done it a bit quick, but that's okay. Yes, so please type in the chat box. Is this fine to all of you? If you take a square common from these two terms, you have 1 minus sin square theta, so that's cos. So let's see, when you calculate this integral, we have the reduction formula of course to get this part. So it's like a power 4 or 1 by 3 times a power 4 into, so this integral is something like this. It's 4, so 4, 3, 2, 1, that's it. Okay, and what is the value of k? This is even, so pi by 2. That's the integration value. So if you simplify this, we have 3 and 3 gets cancelled. So pi a power 4 by 4 4s are 16. So this is the value of this integration. So I is equal to double integral over the a y square dy dx is equal to pi a power 4. Radius is a and this is 16. So that's the value of that integral actually. Okay, so this is the value of this integration. But you can also, you would have told this in another form, which without doing this integration, substitutions and all, you would have told it the other way. If you have a complete circle, so let's see, I'll ask you this question, if some of you might have seen this at least. So let's say if you have a circle like this, x, y, so let's say something like this you have here. Fine. So let's see, this is origin. If this is the circle of radius a, if this is a circle of radius a, then what would be the moment of inertia of this circle about this y axis? So if you take this y axis, the moment of inertia of this circle about y axis, does someone have any idea? Does someone have any idea what's the moment of inertia of this circle about diameter? Basically it's x axis or y axis, both are diameters. So moment of inertia of a circle of radius a about its diameter. Some of you have seen this formula. If diameter is d, if diameter length is d, moment of inertia about the diameter is pi d power 4 by 64. Have you seen this anytime? If you have a circle basically, then the moment of inertia of the circle about its diameter, about any one of its diameter, is actually, if that circle diameter is d, then pi d power 4 by 64. Have you seen this? Yeah, okay. Then in such case, if you convert this diameter to radius, you have 2 radius power 4, and ultimately this 2 power 4 can cancel this 4 times, because 2 power 4 is 16, this power 4 if I bring inside, so 2 power 4 and this 64 gets cancelled 4 times. So pi r power 4 by 4 is the moment of inertia of this circle with diameter, okay, about diameter. Now whenever, if this is pi r power 4 by 4, this is a full circle and this is symmetric about both x axis and y axis. So if you take only one portion, if you take only one portion, not the complete, and all four parts are symmetric. So if you take only one portion, the moment of inertia would be 1/4 of this value. Okay, so 1/4 of this value is 16 here. Okay, if you have known this technique without doing this complete integration, substitutions, whatever you have dealt, without doing this, I would have told this value is pi a power 4 by 6 actually directly. Fine, like this. Okay, and people who don't know this, just you can follow the classical procedure for integration, you will get the answer. But if you know this kind of applications, it's like a very beneficial thing to deal with. Okay, yeah, so let's try to solve one more integration which I'd like to show you. The value of integral over a, say x dA, for example, x dA, where a is, again maybe say a is the first quadrant of the circle. Just I'm giving you some notation, that's it. So the first quadrant of the circle x square plus y square is equal to a square is, let's say if I ask something like is first quadrant, so k a by pi, the value of k is dash. Oh, just a second, you delete this, just a second, is like something like is a cube by k, the value of k is dash. Come on, do this question. The value of k is dash. Solve this question actually. I'll give you time again. So is a type, yeah, 150 is good. So start. Come on, solve this question. I put ax here, so this is the circle in the first quadrant. This value is a cube by k. So what is the value of k? Solve this quickly. Come on, solve this. Two. So let's check. Okay, let's check what's the answer. So if you try to solve this, again let's write the system. So this is x, of course, and this is y, origin x y actually here, and it's again the first quadrant of the circle, say something like. So this is x square plus y square is equal to a square. Fine. So let's see. Maybe we can since there is x here, so if we solve with respect to x, it would be slightly comfortable to do this. So solution, I is equal to integral x times, let's take the first integrating variable to be x, okay, and y of course. So if the first integrating variable is x, let us consider a horizontal step in this region. So if you consider a horizontal step, actually because we have decided to take x as the first variable of integration, first variable of integration, then this is something like x is equal to 0, and it is bounded like x is equal to root of a square minus y square. Okay, so x is equal to root of a square minus y square. So let's substitute x is equal to 0 to x is equal to root of a square minus y square. Okay, and what are the least and maximum values of y? The minimum value of y is at any point in this region on this line, so y equal to 0 at all these cases, and y goes to a maximum of a actually here in this domain. Okay, so y goes to a maximum of a, so y is equal to 0 to y is equal to a actually here. So if you substitute, okay, so let's integrate. I is equal to integral y equal to 0 to y equal to a. So when you are integrating with respect to x, this integration is x square by 2, and the limits are from 0 to root of a square minus y square dy. So what does this gives you? Y equal to 0 to y equal to a. This 1 by 2, this 2 I can pull it up, so 1 by 2 times of, now when you substitute the limits, root of a square minus y square whole square is just a square minus y square, and when you put 0, it is when you put x equal to 0, the lower limit is 0, so dy. Let's integrate this, half times of a square y minus y cube by 3 within the limits 0 to a of course. Okay, so if you substitute half into a cube minus a cube by 3, and when you put y equal to 0, both the terms are zeros, so it's like 1 by 2 times of, if you simplify this, 3a cube minus a cube, 2a cube by 3 actually here. So ultimately this 2 gets cancelled, so a cube by 3 is the actual answer. So this value is 3 of course, so the value of k is 3 in this. Got it? And of course when I have framed this question, I know the answer is coming to be 3 because this value is area into x coordinate. So area of this part is pi a square by 4, 1/4 of a circle, into the centroid of this lies on y equal to x, and x coordinate is 4r by 3 pi. So this is the centroid of the, okay, so 4 gets cancelled, pi gets cancelled, so we have a cube by pi. That's how I solved this. I have done some calculation in the hideout basically using this. Okay, so that's how, a cube by 3 actually, so a cube by 3, so that's the value of this constant. Okay, yeah, so now let's see how to solve these integrals. Of course this is slight easy. If you have started working with y, it would have been slightly more calculative in order to do this, but in general this integral whatever we have solved just one question before, pi a power 4 by 16, you see it's a lengthy calculation actually slightly. Okay, so let's observe something called the coordinate transformations. Okay, so let's see how do we do this coordinate transformation. If I is equal to integral over some domain a, then if you have some function f of x comma y, dx dy or dy dx, whatever depending on the limits that you write here, so this integral in one system, of course it's in Cartesian system here, so this can be converted to some other system. So let's say if, or in general if you have 3 dimensions, okay, or else, yeah, let's put 3 dimensions, let's generalize the result. But so if you have one more integral, let's say x y z dz dy dx. Okay, so let's say you have some expression like, when you have this expression like this, if you want to convert into some system, let a new system with variables x, I mean with variables u, v, w is defined such that this function x is some function of uvz, uvw, sorry, v is also some function y, xyz. So y is also some function of u, v, w, and z is also some function of u, v, w actually here. Okay, so this is the case. Like for example, you see, normally if you have the Cartesian system in 2D, if you convert that to cylindrical system or the polar system r comma theta, you will have some form like x equal to r cos theta and y is equal to r sin theta. So in general, you can observe this x is some function of r comma theta and y is also some function of r comma theta actually. Of course, we know in case of exact cylindrical coordinate systems, this function of r comma theta is nothing but r into cos theta, and this function y of r comma theta is r into sin theta. Okay, so in such case, let's say instead of r theta you have some other transformation, maybe some variables you have defined. So this x, y and z is what you got. Okay, then integral over the domain, or basically over some volume, f of x, y, z, dx, dy, dz or dz, whatever, depending upon the limits again, you right. So this value gets converted to integral over the same domain, f of u, v, w. So basically you can write this x, y, z, because x you can replace in terms of u, v, w, y you can replace in terms of u, v, w, z also you can replace in terms of u, v, w. So this complete function, whatever you have, gets converted to the form, gets converted to some function of u, v, w actually, into determinant or modulus of this j. So we'll see what is that j, times du, dv, dw actually. Okay, so let's say into du, dv, dw actually here. Okay, so x comma y is what we have converted, and so something like this. So where this j is, mod j is nothing but absolute value of okay, so this is absolute value of determinant of the Jacobian, or determinant of Jacobian actually. You can say this is Jacobian dou x, y, z with respect to dou u, v, w actually here. Okay, so this Jacobian is basically the scaling factor, and that scaling factor is considered by this partial derivatives actually. Okay, so let's see, I'd like to tell you one thing, where I'll just first give this Jacobian of x, y, z with respect to u, v, w is given as j is equal to dou x, y, z by dou u, v, w, and this is equal to the determinant of dou x by dou u, dou x by dou y, I mean dou v, dou x by dou z, dou w, sorry, and dou y by dou u, dou y by dou v, dou y by dou w, dou z by dou u, dou z by dou v, dou z by dou w actually here. Okay, so this is the Jacobian value of course. Okay, so that's the Jacobian, and in exam when calculating, let's see if this question turns up. Okay, you are calculating, don't waste your time on deciding whether x is along this or x is along this. It doesn't matter whatever the way you write. If you write dou x by dou u, dou x by dou v, dou x by dou w, dou y by dou x, dou y by dou v, I mean sorry, dou y by dou u, dou y by dou v, and dou y by dou w, and similarly here the determinant do not change, because determinant of a matrix is same as determinant of its transpose. Okay, so this value do not change. So this is basically the Jacobian is what we get. Okay, so physically this Jacobian talks about the scaling factor in domains. So this talks about the scaling factor. Okay, so this is the Jacobian of course. So let's see, in if you deduct this to 2 dimensions. Okay, so let's say if you downgrade this to 2 dimensions, I'll show you a few things. If you have let in 2D, and let's say the conversion is from Cartesian to polar, Cartesian to polar coordinates actually here. So if you do this Cartesian to polar conversion, you will observe something. I is equal to integral over a f of x comma y dy dx or dx dy whatever, or let's say dy dx whatever. Then in fact this dy dx is basically dA, of course. Okay, why we are using Jacobian? When you convert from one Cartesian to another Cartesian, there are scaling factors which comes up, which you will see by using this. Okay, so let's see how we are going that. So in a domain A, if you want to integrate this function, okay, dy dx, of course, if you want to convert this into some polar coordinate system, you might have seen this. If you convert to polar coordinate system or the same area A, this function gets converted in terms of r comma theta. So some function terms of r comma theta. Instead of dy dx, you write it as r into dr d theta. Yes or no? Correct? The elemental area in case of polar coordinates, you write it as r dr d theta. From where this excess r came inside? Because ultimately, if you are converting something in terms of x comma y to r comma theta, for dy dx here, you should have ideally got dr d theta, correct? But sorry, my internet connection is stable. Isn't stable today, it's buffering. Okay, fine, no issue. Just sorry. So try to follow as much as possible. Okay, so let's see. First of all, when you convert this x in terms of r comma theta and y in terms of r comma theta, this function gets modified as capital F of r comma theta. Just y is fine till then. But this dy dx, when you convert to polar, it should ideally give you dr d theta, correct? It should have ideally given you dr d theta. But from where this excess r is coming? That's the question. Okay, and this r is exactly the result of that Jacobian, and this r is a scaling factor. When you convert this dy dx to polar, it turns out to be this r times dr d theta. Okay, so this r is the multiplication factor, and this value is always positive, of course. That's why I have put in the general transformation, I have put a modulus value. Okay, so this is absolute value of Jacobian actually. So let's see. This is r and dr d theta, of course. R is radius, which is always positive. In general, if you have a domain D, let's say, or area A, if you have a figure here, so in general in Cartesian, what you do, you will take dx and dy, and you will represent your dA with this. Okay, so this is dx dy. But in case of polar coordinates, see, the choice of choosing the coordinate system is your comfort. Okay, means basically either to solve a question in xy coordinate system or r theta coordinate system, it depends on your comfort. But this area remains here physically. Yes or no? Correct? Means if you plot a region, whether you take Cartesian system or you take r theta system, it doesn't matter, the area stays there itself. Correct? Only the value of the coordinates, these things change depending upon the coordinate system you choose, but physically the area is present at the same spot. Yes or no? This area which is here will stay there, whatever the coordinate system you choose for analysis. Right? Now, when you are trying to choose this coordinate system, if you choose Cartesian, you have this dx into dy, area of small rectangle. In polar, how do you choose? You will choose this as some area like this. Okay, so in polar coordinates, such that this length is dr, of course, and this angle bounded is d theta. So if this angle is d theta, this length is going to be, or this length, if this dr is very small, one of these lengths is equal to r times d theta. Correct? That's what you have. So when you take this small elemental strip area, it becomes dr times r d theta. That's why one r comes as excess if you are considering same dA in Cartesian and in polar. Got it? Yes or no? Please type it in the chat box. Like what I have told is, and r theta, of course. So if you have a domain like this D, then if you want to take a small elemental area in this domain, the way you would do that is, so let's say this is the elemental area what you are focusing on, let's say. So this is the elemental area. Then this elemental area can be chosen, like how dx into dy can be chosen at any spot in this. Similarly, this elemental area can be chosen at any radius and at any angle theta. So let's say if this angle which is included is d theta, then this length of the arc is nothing but r times d theta. Okay, so this length is going to be r d theta, of course, and this is a small increment in radius, so this is dr. So if you assume it's almost like a rectangle, because this d theta is very small, so there is no much, and di is also very small, so that there is no change in length between these two arcs. Let's say they are almost equal. Okay, then the area of this, if you neglect the small curvature, then this is almost like a rectangle, and the area of this rectangle is dr times r d theta. Okay, so that's why when you convert this dA, in Cartesian you have just dy dx, but in polar you have this multiplication of r. So that's why when you do transformation of coordinates, you will always end up with some factor here. Okay, so that's the reason. Normally in case of spherical coordinates, it's r sin theta. Anyway, we are not going to do spherical in this particular course, but I'm just trying to tell you Cartesian to polar conversion. Okay, so this is r dr d theta. That's why r comes in x. Okay, so in general for any coordinate system, the value which comes excess is given by this Jacobian. Let's check. Even for Cartesian to polar, the Jacobian value will exactly come r. Let's do that. So for conversion from Cartesian to polar, for conversion from Cartesian to polar, actually coordinates, you know, like x is equal to r cos theta and y is equal to r sin theta. So let's say if you calculate the Jacobian, for example, Jacobian of x comma y with respect to r comma theta. Okay, so which is dou xy by dou r theta, and this is equal to the determinant dou x by dou r, dou x by dou theta, dou y by dou r, and dou y by dou theta. This is what I have told you. Okay, then if you calculate this determinant, let's check what do you get. Dou x by dou r. So what is dou x by dou r? If you differentiate this term partially with respect to radius, theta is constant, so cos theta is constant. You get cos theta. Dou x by dou theta. So if you differentiate this with respect to theta, r is constant, and derivative of cos theta with respect to theta is minus sin theta. Okay, then dou y by dou r is sin theta, and dou y by dou theta is r cos theta. If you calculate this determinant, the value is r, right? Because r cos square theta minus r sin square theta. So r, if you take common, you have, again, let's see, if you take r common from this column, you have cos square theta minus sin square theta, which is plus sin square theta, and at any given value of theta, this is an identity, so this value is always 1, so the value is r actually here. So which means if you want to convert any integral with some function f of x comma y dx dy to some function, because obviously this function will change now, so some function of r comma theta, and if you want to write dr d theta, definitely you should write Jacobian value here, which is r actually. So that's why physically, mathematically doing this Jacobian or physically understanding this construction with r, both are same. Okay, dA is equal to this. Clear to all of you? Yes or no? Please type it in the chat box. Did you all understand the coordinate transformations? I'll show you an example, of course, but physically or basically mathematically in the basic funda, what's happening, can you all understand? Okay, did you all understand why this Jacobian comes out? This Jacobian is basically the scaling factor. Okay, so this dA is same as dy dx, but it's not actually equal to dr d theta. It should be multiplied with this factor r, of course. Yeah. Okay, so now let's see. Let's work out an example. So ultimately this gives you the Jacobian value to be r. So that's why in Cartesian to polar we use this conversion factor. Okay, similarly if you do for 3D x, y, z, two spherical coordinates like x, y and z system, I mean this r theta and phi system, you will see r sin theta will be the Jacobian actually. Okay, so which again generally not asked in the gate limits, of course, these conversions. So let's see. Let's work out an example. So let's see, I is equal to, so let's take this example. Okay, so which you have taken, so the value of integral y square dy dx. Dy dx means basically dA, where over a, where a is region of x square plus y square is equal to a square in first quadrant. Okay, so in first quadrant is dash. Okay, so let's say you want to calculate this value. Then if you calculate this, let's see solution. So let's plot the function x square plus y square equal to a square in the first quadrant. Origin x and y, of course, and you have the curve like this is x square plus y square is equal to a square actually here. Okay, so if you have that curve x square plus y square equal to a square, and this is the region what you have, then this is the complete region. Of course, I'm hatching it so that you can observe something. Okay, so this is the region. Now in this region, if you want to calculate this integral, I equal to integral over a y square dy dx. So converting to polar coordinates, converting to polar coordinates. So if you convert to polar coordinates, you know, at any point x equal to r cos theta, y equal to r sin theta. So this becomes I is equal to integral over the region A. The region A means as usual. This y square is actually r square sin square theta, correct? Because x equal to r cos theta and y equal to r sin theta. So y square is actually r square sin square theta. So here f of x comma y, small f of x comma y is y square. So capital F of r comma theta is r square sin square theta. So the function gets modified accordingly. Okay. Then this dy dx, just now we have seen, that can be modified as r dr d theta, of course. Okay. So this can be written as r dr d theta, of course. So let's evaluate this integral. So I is equal to integral r square into r. So it is r cube sin square theta dr d theta actually. Now tell me, if you want to bound this region, the least value of radius is 0. Means if you take a small radial curve. So let's see, if you take a small radial curve, of course, maybe which color I should use? Okay, so pink, I think you can see. So if you take this curve, so this radius r is equal to 0 at this point. At any point on this curve, it is bounded by this one. In polar coordinates, every point on this curve is just given by r is equal to a, correct? Yes or no? The polar form of this equation is nothing but r equal to a. So if you do squaring on both sides, r square equal to a square, so x square plus y square equal to a square actually. That's it. Okay. So this radius changes from r equal to 0 to r is equal to a, and a is a constant value. Okay, because it's a circle in this case, so a is actually constant. You either take this strip in any orientation, it doesn't matter. The lowest value of radius is always 0 and the highest value of radius is always a, of course. Okay, so it is bounded. Now what about theta in the first quadrant? So we are sitting in the first quadrant, so you can move this region from here to here anywhere. So the least value of theta you can have is 0 when it matches with x-axis, and the highest value of theta you can have is pi by 2. So theta equal to 0 to theta is equal to pi by 2, of course. So if you calculate this integral, first of all tell me one thing. In this integration in polar coordinates, the limits on the integrals are constants or is there any variable involved? There are 4 limits. All the 4 limits are constants or is there any variable in that? Normally this r equal to a is a constant, okay, because it's a circle in this case. So please tell me, these 4 variables, are they constants or do they involve any variable? Come on, a bit faster. So tell me quickly. Are they all constants or is there any variable? Theta is variable, r is also variable, right? But normally if you look at the limits 0 to a, 0 to pi by 2. R and theta are variables, but I am asking about the limits on the integrations. Okay. Yeah, theta is variable, I do understand, but the value of the limits on the integrals. I'm asking about the values of the limits on the integrals. They are constant, right? So 0 is constant, a is a constant in this case, pi by 2 is also constant. See, basically in Cartesian you have seen something like this, right? So these are functions of x actually. Okay, but we have seen few cases where x is equal to a, 2x is equal to b, y is equal to c, to y equal to d. We have constant limits in that case, correct? I'm asking about the limits. They're constants, right? In this case, the limits are constants, but in this case, the limits are not all constant because you have a variable involvement here. Okay, so that's what I'm asking. Obviously, you write limits for only variables, right? Nobody writes limits for constant. Okay, but I'm asking the value of the limits are constants. Okay, so if they are constants, can I do something? Look what I can do. By the moment you recognize that they are constants, you can actually split it, correct? So all limits are constants. Since all limits are constants, this implies I can be written as, I can split it integral theta equal to 0 to theta equal to pi by 2 sin square theta d theta into integral r is equal to 0 to r equal to, I have told this in the last class, okay, and we have solved some examples as well. So r cube times dr, this is what you get, right? I can do this. So the value of the first integral, you can use reduction formula. So what is the value of the first integral? It is 2. So 2, 1, that's it. Value of k, so this is even, so k is pi by 2 because this integration is from 0 to pi by 2. So this is the value of the first integral. Value of the second integral, this is r cube, so r power 4 by 4, but if you add the limits, it's a power 4 by 4, that's all. Correct? Because this integration is small r power 4 divided by 4 within the limit 0 to a, so if you substitute, it gets a power 4 by 4. So if you simplify this, pi a power 4 by 16, that's all. A single go. One step we have got the answer, okay. But whereas there in Cartesian, the same integral, if you solve it in Cartesian, we have got the answers pi a power 4 by 16, but after doing a lot of integration, then substitution and simplification all, okay. So after this we got the answer to be pi a power 4 by 16, but if you convert this Cartesian to polar because of coordinate transformations, you got the answer in a single line actually, okay. So that's the power of coordinate transformations, because physically the things remain same, the same area, the same quantity we are calculating, but the choice of coordinate system helps many times, okay, in resolving the integral. Got it? Yes, is this clear to all of you? Everyone? Ajit, Shravan, Shrikant, of course many of you who did only these. Okay, fine. So what I'll give you is just check this quantity, okay. So check whether this is also coming or not. You take x equal to r cos theta, r dr d theta, r is changing from 0 to a, theta is changing from 0 to pi by 2, calculate the integral, you will get the answer, okay. Yeah, Vijay. So let's do something on volume integrals, okay. So all this is 2D integrals we have done. Basically let's go for 3D. It's very generalization, that's why I have thought of keeping it at the last. In fact, I would have taught this much detail in vector calculus, so we can talk about this in much detail in vector calculus, of course. So let's see volume integrals actually. In general, or if you have written volume integrals, let's continue. So I is equal to integral over the volume, say some function x, y, z, dz, dy, dx. So normally you have done 2 variable integration, okay. So now it's 3 variable integration. The idea is very simple. Look, I'll give you in general, normally in multivariable calculus you have the standard result, like let's say you have n integrals on some function of x1, x2, x3 and so on, xn, dxn, dxn minus 1 and so on, dx2 or dx3, dx2, dx1. If you have this integral and you have to evaluate this integral, okay, normally in n-dimensional space. If you have this n-dimensional space and if you want to evaluate this integral, how you evaluate is, let's write one more integral here. So if you choose your first variable of integration to be xn, okay, so if you choose your first variable of integration to be xn, then let's write something like this. Then let's see the limits on the inner integral. If you choose this first variable of integration to be xn, this integral should definitely consist limits of xn, okay, but this xn limits should be functions of all preceding variables. Okay, so let's see, xn is some function of, say, some function of xn minus 1, xn minus 2, and so on, x3, x2, x1. So this is what you get. Similarly here, this xn is some other function, say this is alpha function maybe, and this is some function beta of xn minus 1, xn minus 2, and so on, x3, x2, x1. So this is what you have. Okay, similarly the integral, which is penultimate integral, let's say if you have the integral here something like this, then this tells you, since the second variable of integration is xn minus 1, the next integral xn minus 1 consists some function of, say, phi of xn minus 2, xn minus 3, and so on, x1. Similarly here, this xn minus 1 is equal to some function of xn minus 2, and so on till x1 actually, and so on. This integral finally leads to x1 or x2 is equal to some function, say h of x1, x2 is equal to some function, say like maybe some gamma of x1, and finally the last integral consists constant limits. Okay, so the last integral consists of the constant limits, x1 is equal to a to x1 is equal to b actually here. So this is the general way of writing limits in a n variable integral in general. Okay, so when you have written in two variables, what we have done, we don't have all these things, we just have these two, and we have only these two, and this function is also only of x1, x2. Okay, that's it. So that's why this functions we have written in terms of the other variable, and we have written the constant limits at the end actually. But in general, this is the way how you can calculate a n dimensional integral actually. Okay, look, I'll explain you. For n equal to 2, okay, so let's see, for n is equal to 2, so let's say if there is only involvement of two variables. Okay, so in this function you have involvement of only two variables, n value goes up to 2. Okay, then I is equal to integral over some domain. If you have f of x comma y dA, we have actually written this integral as f of x comma y. Now when you write dy dx, or let's say n equal to 2, we have written f of x comma y. Instead of x comma y, we'll choose x1, x2. So f of x1, x2 times dA. So this is f of x1, x2. Okay, so this is x1, x2, of course, f of x1, x2. Then this dA we have written as, let's say dx2 is your first variable of integration, and dx1 is the next variable of integration. Okay, then we have written this x2 as some function of x1 and to some other function of x1. You remember we have written y equal to some function of x, y equal to some other function of x, and finally the x limits we have written as some constant up to this. So this is what we have written. Okay, like replace just x1 with x and x2 with y, you will get what all we have done till now. Yes, but I'm just showing you the general form. Okay, is this clear to all of you? Yes or no? So please type it in the chat box. Yeah, got it. So if you replace x1 with x and y with x2 or x2 with y, then what all we have done till now, you will get it. Okay, for n equal to 3, what happens? Look, for n is equal to 3, you have I is equal to, let's say it's a volume integral or some volume v, f of x1, x2, x3, dx3, dx2, dx1. So let's say you have this. Okay, so once you have this, we write the limits in such a form that f of x3, x2, x1. So let's say you have dx3 chosen, dx2 and dx1, let's say. Okay, so the first variable of integration, maybe you have chosen this dx3. So ultimately here the limits would be x3 is equal to some function of x1, x2 to some other function of x1, x2 general. Okay, and now coming here, the limit next integrating variable is x2. So the value on this integral is x2, but now before x2 you have only one variable x1, so just write it as some function of x1 to some other function of x1. And obviously the third integral has x1 limits, so it do not have any variable, so just write some constants. So let's say a to b. So this is the way how you keep writing the limits, of course. Okay. So the next step I use partial integral. Yeah, of course. Okay. So when you are integrating this, you have to, if you are integrating with respect to x2, okay, so you have treated except x2, you have treated this all other variables constant. Okay. Similarly, if you are differentiating, if you are integrating with respect to x3, you will integrate partially with respect to only x3. You will treat x1, x2 constants. Okay. At each step, so in general, now I hope you understood this. This xn will involve the limits in functions of all the variables which are to the right side of xn actually. Okay. Similarly, when you come to xn minus 1 limits, so from n minus 1, all the limits to the right, it starts from xn minus 2, n minus 3 and so on, it goes till x1. Similarly here, when you go to x2, finally, when you go to x2, there is only x1 left. So these functions are only of x1. Okay. And finally, you have constant limit. That's the general integration. Clear to all of you? Yes or no? Please type it in the chat box. Now, when you understand it for n equal to 2, n equal to 3, so similar discussion can be extended for a general value in n dimensional space, which is this. Clear to all of you? Yes? Fine. Yeah. So if you have understood this, I'll give you one homework question, which maybe you can bring it tomorrow. You can solve it and bring it tomorrow. Let's see. The value of integral 0 to 12, let's say, integral 0 to 12, integral 0 to x, integral 0 to x, integral, what I can do is maybe something like equal to, let's say if I define a plane like this, the height of the plane is, yeah, so let's say this is 0 to 6 minus x minus y. Okay, so yeah, 6 minus x minus y, dz dy dx, let's say, is dash. So solve this question as homework question, try it by yourself. I have given you all the inputs, what all you need. So solve this question as homework. So you have seen how to do the questions. So obviously the same technique. So first you'll integrate with respect to z, then substitute the limits, what all you know you can do. Okay. So calculate this question as a homework for tomorrow. Okay. So anyway, much more emphasis on volume integrals, like how to choose the prism in between and how to write the, if volume is given, how to write the z limits. Okay, so these things we'll discuss in much detail in vector calculus, because there things can be solved relatively easy by using something called Gauss divergence theorem, where we calculate the volume integrals of scalar functions. So there at that point we'll discuss in detail. Okay, in much detail of course, but in general this is the way to calculate an integral of n dimension. Okay. And normally for this kind of stuff, you can refer books like Apostol. Calculus by Apostol is one really good book, which many universities in India follow. It is in 2 volumes. First is of single variable and second is generally of multi. So Calculus by Apostol. So this is a nice book. It's very what is the meaning of 6 minus x minus y? We'll see. Normally if you have a plane x plus y plus z is equal to 6, then z can be written as 6 minus x minus y is what we write as the limits. That's what I'm telling you. Geometrically, what does it signify and how, when a volume is given, how to write the limits, we'll see that in the vector calculus. But as of now, if some integration is given like this, okay, then how to solve, I have given you the idea. So just do this. So in fact, practically this tells you, if you have a plane, okay, if you have a plane, define something like this, okay, and if you have the coordinate systems, so let's say you have the coordinate system x, so let's take a right-handed coordinate system, and this is z actually in this case. Okay. So let's see, if you have this origin x, okay, x, y, z, the right-handed coordinate system, let's take, and y is equal to x, so y equal to x line would come up something like this. Okay, so this is y equal to x, and x is going from 0, so which is basically this yz plane actually, so going till 12. So if you look at this part, so this is x is equal to 12 line, and x is equal to 12 is basically having a constant value here, constant value of x, and y equal to 0 to y equal to x. So basically y equal to 0 is this xz plane, so this is y equal to 0. And if you construct this prism, actually if you construct this prism, you construct this prism, of course, okay. So something like this. It's the line which is parallel to this, and since geometrically have asked, what does it tells you? Just giving this idea to you. That's it. So basically this plane is on this plane actually, and this plane is, let's say if you have some plane, let's say for example ax plus by plus cz is equal to d actually here, okay. And this plane need not be exactly straight, it can have certain orientations, whatever, that's a general equation, but the top edge is restricted by this plane actually. So in such case, if you get the value of z, it turns out to be something, some constant like d minus d by a, or basically this, if you write z value from this, it turns out to be d by c minus a by c times of x minus b by c times of y, okay. So something similar to this I have given here. So again we'll see how to write the limits and all when geometry is given. Basically you will construct a prism inside, and you will see the bottom of the prism is always bounded by this plane where z is equal to 0 because it's xy plane. And of course here the plane is not exactly this, but in general if you construct a proper plane, okay, so maybe instead of this, what we can do is I'll try to construct a plane which involves this actually, okay. So there is a inclination which you can have, just make this a bit shorter, and then make this line, make these lines actually here. So let's see, construct a line like this. So I hope you can see now this is a plane actually, and this plane, let's say if it's making an intercept of 6 at this point, okay, and x intercept is basically 6, y intercept is also 6. So let's say there's a plane like this which is like a trapezium, then this plane has some coordinates, okay. So then this plane is given by z is equal to 6, so xyz axis. So in such case, basically if you draw a prism such that this prism is always having the bottom face z equal to 0 and the top face is bounded by that value of z, okay. And once you write this integral limits, then once you project this onto xy plane, the new limits of y will be 0 to x and x limits would be 0 to 12, okay. So there's certain bit of geometrical impact again which we will deal in much detail when we come across this multiple volume integrals in vector calculus, okay. Thereby choosing the Gauss divergence theorem, we'll see that things get simplified a lot. At that point I would give the correct geometric description of all these things, but right now if something is given like this, how to calculate, okay. So that's what the main intention is here. So just calculate this in tomorrow's class, okay. So we'll start differential equations tomorrow again. We'll start the differential equations in tomorrow's class. So let's see, in today's class what we have seen is basically like okay, yeah, you can calculate this also maybe. So this is also homework. Of course I think both are two different functions. Z is changing, yeah, z is changing, so just calculate this. So in today's class we have talked about multiple integrals actually, so multiple integrals, and most importantly coordinate transformation. Coordinate transformation. So these are the things which we have discussed in detail, and in tomorrow's class we'll meet again and we will start a new chapter which is differential equations, okay. So we are going to start this differential equation in tomorrow's class. So that's all for today. If you have any quick questions you can ask me, or else it's fine. So is this clear? It's like offline class, very interesting, informative, important, and interactive. Yeah, thank you. So just respond to the questions. That's the main thing. Because if you don't respond, then ultimately, this being an online class, I won't be able to catch your emotion, okay, and eye contact. So I feel like everything is understandable, okay, but guys have to be little proactive. So fine then. Yeah, so we'll meet tomorrow at again 7 p.m. and we'll start the new chapter, differential equation. Okay. So fine then. Thank you all. We'll meet